Hi everyone, welcome back to the another video of Engineers Academy. So guys, over here in this video we are going to talk about the another thermodynamic cycle that is introduced by Mr. Sadi Carnot in 1824. So basically he was the military scientist, he was the inventor behind this Carnot cycle and Carnot engine. So first of all, you have to understand that this particular Carnot engine is totally ideal engine and there is no practical engine he manufactured. He just gave a theory regarding this particular Carnot cycle and Carnot engine. So guys, basically in our heat engine, the problem is that when a piston reciprocates into engine cylinder, the heat gets lost over here due to the friction of the piston into the engine cylinder. So the energy gets lost over here due to friction. Also guys, this particular walls of the engine cylinder are good conductor of the heat. So heat will transfer through the walls to the atmosphere. So there will be the another loss of heat over here in heat engines, in conventional heat engine. So guys, this particular Sadi Carnot, he proposed that if we isolate that particular engine cylinder through all the sides, so that we can increase the efficiency of the heat engine. Also he proposed that if we neglect the loss of friction over here due to the piston reciprocation moment of the piston, so we can increase the efficiency of the heat engine. So basically he just proposed how can we increase the efficiency of the heat engine, and he proposed a new cycle that is nothing but the Carnot cycle. So guys, over here in this video we are going to talk about this Carnot cycle and Carnot engine. So guys, please watch my video till the end, and guys, if you're new to my educational channel over here at Engineers Academy, you can subscribe to my educational channel, and guys, please press the bell icon. So guys, let's begin with our today's topic, that is nothing but the Carnot cycle and Carnot engine basically. Just like the IC engine which works on the Otto cycle, over here this particular Carnot engine works on this Carnot cycle. So guys, basically Carnot, he was a scientist, he just neglected all the losses over here which occurred in heat engine to increase the efficiency of the heat engine. So guys, over here in this case of the Carnot engine, there are the two main stages, that is nothing but the expansion stage and the compression stage. So in a particular engine cylinder, he just made that particular engine cylinder isolated from all the sides, such as no heat will escape from the engine cylinder to the outer atmosphere. Okay, at the bottom of the engine cylinder, he just made a provision that the hot body will come in contact with that bottom of the engine cylinder, so that the heat will get absorbed, and due to that the piston will move, that is the expansion will take place, and after that expansion the insulating pad will be come in contact with that particular bottom of the engine cylinder, so that the total system gets closed and no heat will flow from the bottom of the engine cylinder. And at the last stage, that is at the compression stage, that particular insulation pad gets removed and the cold body which comes in the contact with that particular bottom of the engine cylinder, and that particular cold body absorbs the residual heat, or else we can call it as sink basically. So it absorbs all the heat. So guys, this particular process, this particular cycle continues itself, and this particular engine can be called as the Carnot engine. So basically this is the ideal engine, and we cannot construct an engine which works on this particular Carnot cycle. So basically over here you can see that this is the pressure, volume and TS diagram of the Carnot cycle. So basically what is Carnot cycle? So this particular Carnot cycle is having this four type of thermodynamic processes. So the first one is the isothermal expansion, followed by the isentropic expansion, that is we can call it as the reversible adiabatic expansion. The third process is the isothermal compression, followed by the isentropic or reversible adiabatic compression. So guys, the process 1 to 2 is nothing but the isothermal expansion. Over here the isothermal is the temperature constant. So over here the expansion will occur. It means the hot body comes in contact with the bottom of the engine cylinder. The heat flows from the hot body to the engine cylinder, and due to that heat the expansion will occur. As the expansion will occur, pressure gets released, like the pressure will reduced over here, and the volume will increase over here. So guys, over here when the piston moves due to that heat, the expansion will occur over here, and that particular expansion is the isothermal type of expansion. It means the temperature will constant over here. So guys, over here you can see that this is the TS diagram. The temperature remains constant from process 1 to 2. From process 2 to 3, as the 2 to 3, at this particular point, piston is far away from the hot body, and in this case the temperature inside the cylinder falls down, but we have insulated the cylinder. It means the total heat will remain constant over here. In this case, the process will be reversible adiabatic. The total entropy, the total randomness of the system will be constant over here. So process 2 to 3 is nothing but the isentropic expansion. So over here, in this case, the entropy remains constant. As you can see over here in TS diagram, the entropy from 2 to 3 will remains constant over here. And guys, from 3 to 4, the compression will occur. Now over here the compression will be the isothermal compression. The temperature will remains constant, but over here the entropy of the system will increase. Over here the internal energy of the gas will increase. As we have seen in our previous videos, when we compress a gas, the internal energy of the gas will increase. And guys, at this particular point, the volume reduces, the pressure increases. So over here you can see that this is the curve on the PV diagram. So now this particular 3 to 4 process is the process of the isothermal compression, and after the isothermal compression, the adiabatic, reversible adiabatic compression, or else we can call it as isentropic compression, will occur. Now over here in this case of isentropic compression, the entropy of the system will remains constant. In case of the isothermal compression, the entropy of the system increases, but after a period of the time, the entropy remains constant and the temperature increases as this particular piston comes in contact with the hot body. So the temperature increases over here, and that particular at the end of the cycle, that is from 4 to 1, the cycle is named as this isentropic compression. That will get the initial pressure, initial volume and initial temperature at point 1. So guys, over here at point 1, the total cycle gets completed over here. Now guys, over here let's talk about the work done and the efficiency of this particular Carnot cycle. So work done is nothing but the heat supplied minus heat rejected. So over here the heat supplied, we have supplied the heat at the process of 1 to 2, that is nothing but the isothermal expansion. So guys, over here the expansion is taking place and we have supplied the heat at this particular process 1 to 2. So we can calculate the total heat supplied by using the formula, that is 2.3 m into R into T1, that is at the higher temperature, into log V2 by V1. So V2 by V1 is nothing but the expansion ratio, as this is the expansion process. So V2 by V1 can be called as the expansion ratio, and we can denote by using R. So over here in this case, the compression ratio and the expansion ratio is the same through all the cycles. So over here the formula becomes 2.3 mR T1 into log R. So that is the heat formula for the heat supplied. Now let's come to the heat rejected. Now over here in this heat rejected case, the heat get rejected in the process of 3 to 4 basically. So guys, we can calculate the heat rejected over here by using the same formula, that is nothing but the mR T, that is the heat gets rejected at T3. So we can use this particular temperature 3, that is the the lowest temperature over here in this particular thermodynamic cycle. So that the formula for heat rejected will become like 2.3 into mR T3 into log, that is V3 by V4. So over here the compression will occur, so that's why the compression ratio is the same. So we can write it down like 2.3 into mR into T3 into log R. So guys, over here the work done will be heat supplied minus heat rejected. So the total formula becomes 2.3 mR T1 into log R minus 2.3 mR T3 into log R. So that will be the total work done. Now let's talk about the efficiency. The efficiency is nothing but the work done divided by the heat supplied. So guys, over here in this case, the total efficiency of the system we can calculate, that is the work done upon heat supplied. as we have got the formula for the work done, we can we can write it down, the formula for the work done divided by the heat supplied. So guys, in the numerator and denominator we got the similar parts, we just cut it down from the numerator and the denominator, and we got the ultimate formula, that is nothing but the T1 minus T3 divided by T1. So T1 gets cancelled, we'll get the formula as 1 minus T3 by T1. So that is nothing but the formula to generate the efficiency of the Carnot cycle or else Carnot engine. So guys, in this particular way, this particular efficiency of the Carnot engine is very much on a higher side than that of the other cycles. So guys, in this video we have seen this particular Carnot cycle and Carnot engine. This is how this particular Carnot assumes everything, and then he generated this particular Carnot cycle and Carnot engine. But basically this is the ideal cycle. We cannot construct an engine which works on this particular cycle. So guys, this is all about this Carnot cycle and Carnot engine. I hope you understood this particular Carnot cycle and Carnot engine. Also guys, if you like my video, please hit like, comment and share. Guys, your likes will really motivate me to make more of such educational videos, guys. So guys, thank you for watching my educational video over here. Please do subscribe to my educational channel, Engineers Academy.